Hello and welcome to another exciting lecture for stats. In this lecture we're going to cover measurement, research methods, and summation notation. It's essentially an overview of an introduction to stats. So the learning objectives for this lecture are to define the basic terms in statistics, though that's going to be an ongoing learning objective throughout the course, to identify different types of variables, and there's a few different things within that we'll look at, identify different levels of measurement, differentiate between a population parameter and a sample statistic, describe the main differences between descriptive and inferential statistics, and finally to utilize the summation notation in computations. So as I'll say, this is not a math class, it's a stats class, so knowing the concepts and knowing why you're doing the stats is more important, but at the same time we do math in the class, and that's where this last one will come in. So let's look at the first thing, and that is what research in the behavioral statistics entails. And the process that we do when we're doing research is to first identify a problem or a question. And how would you go about doing this? Well, that can be answered in many different ways. To identify a problem or a question, maybe it's something that you've read in a news article, and that gets you to thinking about something. Or maybe it's something you read in a journal article. Maybe you read research articles and that gives you an idea. Maybe it's just something you see in the world around you. Maybe you see that someone acts a certain way and you want to know why that person or if other people also act that way. So when we identify a problem or a question, that is actually can come from many different sources, many different things that lead us to, okay, well, this is something I want answered, or this is a problem that we need to identify a solution to. And that is the first step in research. The next step is to form a hypothesis. So when we form hypotheses, and we'll talk about this later, but forming hypotheses is where we essentially start looking at, well, we think something is a certain way. We've identified the problem. Why is that person acting that way? Or do other people act that way as well? So that is our problem or our question. Now we form a hypothesis. We hypothesize that other people do act the same way as this person. Or we hypothesize that this person acts this way because of X or because of Y. So that's where we form our hypotheses. And when we form hypotheses, we're forming this based on the information we have. We will then, in this process, maybe do a literature review, maybe look at what other people have done research on. So when we form hypotheses, we don't just form them out of the blue. We form them based on what the evidence has before us, like research articles, like prior research that's been done on the topic. So the example I've been using, why is that person acting that way? We hypothesize that they act that way because maybe they have depression. So if that's the hypothesis, then we've put that down. Well, we formed that based on maybe we looked at a bunch of research articles and it says that people with depression act a certain way, and you see that that person is acting that way, the same way as people with depression act. So we form that hypothesis, that is that the person is acting that way because they have depression. Then we design and run an investigation. Now I've been giving an example of why that specific person acts that way, but let's say, why do many people act that way? And we're going to design and run an investigation, and we're going to find people, maybe people that both act that way and don't act that way, and we're going to investigate that on them. We're going to test to see if in a sense, what it comes down to is we're testing to see if the people that are acting that way have depression and the people that are not acting that way don't have depression. That type of thing. So then after we've run that investigation, and designing and running that investigation is what we'll do in methods. Now after that, we analyze the data to test the hypotheses, and that's what we'll do in stats. So designing and running the investigation, forming the hypotheses, that's methods. Analyzing the data, that's stats. And then once we've analyzed the data, we need to draw conclusions about it and basically look at how that can be viewed in the wider context. And that is, in a sense, making generalizations. And that's another thing we'll cover in both methods and stats is, okay, the stat says this, what does that really mean? Then we need to communicate the results, and this is where you write up your research report and get it published. So we'll be doing that in methods throughout the semester. And finally, you should replicate or extend the findings. So you can't just stop when you get done with this. You need to keep going beyond this and looking at future research, looking at it more in depth. Maybe the results we got, and this is one thing we'll talk about in stats, maybe the results we got were in error. So that's why we replicate it. Maybe the results we got can only be generalized to a very specific population, a very specific subset of people. So we replicate to, let me make sure I've got everything right here. Okay, so we replicate to make sure that we didn't get our results in error, and we extend it so that we can generalize it to more people or possibly look at more in depth, maybe what type of depression the people have. So on this slide is a graphical representation of stats that you're going to see a few times throughout the semester. I'll bring it back up a few times, so we're going to just kind of hit on it briefly now, and we'll come back to it later. It's just a good way to visually represent, not graphically, but visually represent statistics. So first, let's say you have a question, and your question is, okay, what is the age of students at the university or college? What is the average age of it? And are they older or younger than the national average? So the first thing you're concerned with is the population. And the population is all people, places, or things that have the variable of interest. In this case, the variable of interest is age, and it's all people with that age. Our population is the college's students and their average age. So the population is all students at the college. And then within that, you're going to have what's referred to as parameters. We'll come back to this in a minute and describe it more, but parameters are going to be the things that define that population. You've got the mean, the standard deviation, the proportion or correlation. You've got all of these different ones that are going to look at or describe the different things for that population. So these are what are referred to as parameters. Then you also, because we can rarely collect information on all people in a population, when we're talking about the students' average age, we could get everybody's average age. But let's say we're interested in people with depression in the U.S. And when we look at that, we can't get information on every single person in the U.S., at least not to answer that specific question. So what we do instead is we take a sample. And a sample is some of the people in the population. It is what's referred to as a subset of the population. So let's say we were looking at that average age of students. Let's say we took 10 random students. And that 10 random students would be a sample. Or we could take 20 random students or 30 random students. And the terms that we use to describe the sample is what's referred to as statistics or descriptive statistics. And here you'll have, I told you up above was mean, standard deviation, and correlation. Well, these are the same thing, mean, standard deviation, and correlation. Those are just the symbols that denote that it's a sample rather than a population. And these sample statistics are what's referred to as descriptive statistics. We'll come back to descriptive in a minute, but they're what's referred to as descriptive statistics. That's important because what they're doing is they're essentially describing the sample. the mean, which is the average age, or the average. So that is something, the average, the mean, is describing the sample. If you're looking at standard deviation, correlation, things we'll talk about later, those are also describing the sample. But we're not interested in the sample, we're interested in the population. So what we do is we do inferential statistics. We take our sample and our descriptive statistics of the sample, and we use probability theory, which we will come back to in the second segment after this first segment we get done with. We'll come back to and use probability theory. And using probability theory, we'll take these descriptive statistics from the sample and use inferential statistics to make inferences about the population. And we can do this through two different ways, through parameter estimation and hypothesis testing, but we'll come back to that later. So as was described in the syllabus, we can break down the semester into 3 parts. Technically we break it into 4, but we could break it into 3 segments. The first segment is going to be descriptive statistics, and we'll cover that for the first 3 to 4 weeks. Then we've got probability, which we'll cover for 2 weeks after that. And finally, we've got inferential statistics, which I break into half because most of statistics is inferential statistics, but you need to get that descriptive and probability theory first. But essentially the last half of the semester, we will do inferential statistics. My clicker's not working, so I gotta manually change it. We're going to finally get to learning objective 1, which is define the basic terms in statistics. And as I already said, this is a learning objective that is going to take place all semester. That is because, just like in any field, when you first took psychology, you got a whole bunch of terms. In stats, there's a whole bunch of terms as well. But to make it even more complicated, statistics is something that's used in many, many different fields. So because of that, what you end up getting is maybe somebody in chemistry who's using statistics uses a certain term to describe something. Somebody that's in a behavioral science uses a term to describe the same thing, but it's a different term. So what you're going to get is sometimes you're going to have multiple different terms that mean the same thing. And I try and give you examples of this as we go throughout. Your textbook may even have different terms than I use. When that comes up, I try to point that out. I've taken 14 stats classes, so I've gotten to experience a lot of different terms, but because of that, I'm pretty set in the ways that the terms that I use. And there will be sometimes that multiple different terms will mean the same thing. But we will, throughout the semester, be looking at basic terms in statistics. So because we use a lot of words, it's important for you to understand them all. And we're going to cover this today. And we're going to look at types of statistics. We're going to look at the difference between a population and a sample, a parameter and a statistic. We're going to look at experimental design. We're going to look at levels of measurement. We're going to look at real limits and rounding. And we will finish up with statistical notation, looking specifically at the summation notation. Which now gets us to learning objective 2. So it's within that learning objective 1, but learning objective 2 is identify the different types of variables. And you're going to see over the next few slides that there's many different ways to identify different types of variables. So what is a variable first? A variable is anything that can take on a different quality or quantity. The color of shirts people wear, having depression, pain, the type of car you drive, whether it's a full moon or not a full moon. So anything that can take on a different quality or quantity is a variable. Those are all different types of variables you can have. Now we can break this down into, when we're talking about statistics, we break them down into 2 different types of variables, being an independent and a dependent variable. The first one is independent variable. So an independent variable is something that's manipulated in an experiment. It's something that the researcher in an experiment manipulates. So let's say we're trying to see what drugs reduce pain. If one drug reduces pain better than the other. And you have people in for an experiment and you give half of them one drug and half of them another drug. Well, what was manipulated there was the drug they were given. So that's what the researcher manipulated. They manipulated that half got given one drug, half got given another drug. So the independent variable is what the researcher is manipulating. On the other hand, the dependent variable is the outcome variable or the measured variable. The outcome variable is the one which you're assessing. So I gave an example of pain medication on pain, the effects of a drug on pain. The independent variable is the drug given. The dependent variable is levels of pain, how much pain the person is experiencing. So it's the measured variable. And then within that, we can talk about levels. So levels is the different treatment conditions within the independent variable. So in the example I gave, we gave two different drugs, so there's two different levels. The two different levels are the two different drugs. If I gave three different drugs, there would be three levels. If we were looking at crime in a city based on when there's a full moon and when there's not a full moon, well, in that case, what we're looking at the difference of is full moon or not full moon. So in a case that is a pseudo-independent variable, and the levels would be full moon or not full moon. Their dependent variables do not have levels. Even though I just talked about pain level, that's not counted as a level. Dependent variables don't have levels, they just have the measurement that we're taking. In your homework, you're going to have to be able to identify independent and dependent variables. I'll give you a scenario. I'll say something like the lighting, a researcher wants to know how lighting affects test-taking ability. And in that case, what's the independent variable? Lighting, because that's what's being manipulated. The researcher puts them in bright lighting, dim lighting, that type of thing. What's the dependent variable? What's being measured? Well, what's being measured there is their test-taking ability. So the independent variable is the lighting, the dependent variable is their test-taking ability. And specifically on this one, you'd probably talk about their score on the test. That would be the dependent variable, because it's what's being measured. Okay, I said that types of variables can have multiple different things. So we talked about independent versus dependent. Well, within variables, we talk about qualitative versus quantitative. So qualitative variables are variables that vary in kind, but that kind doesn't reflect size or the extent of what's being measured. What do I mean by varies in kind? So varies in kind means you're grouping them together into, another way to say it is varies in categories, varies in kind. So if I was interested in what type of vehicle you drove, that would be a qualitative variable, because you would drive a Ford, a Chevy, a Toyota, whatever one it is. But that would be what you drive would be put into a category or a kind. So all of Chevys would be grouped together into a kind. And if we're looking at it, you can measure a quantity or a number in that kind. So let's say 5 of you drive Chevys, we could put a 5 next to it. But the difference between Chevy and Ford is not something that reflects size or the extent of what's being measured. Conversely, you've got quantitative. Quantitative does vary in amount. It does matter about size or extent of what's being measured. So it has a magnitude. It tells you something about how much of the variable you have. So if I was talking about height, height is a quantitative variable because it is something that's measuring in amount. It's measuring in the distance from the top of your head to the ground. And it does vary in magnitude or amount. So the difference between qualitative and quantitative is varies in kind, It's not something that reflects size or amount, whereas quantitative, it does amount or magnitude is important. All right, let's look at one more difference between types of variables. The next is discrete or discontinuous versus continuous. A discrete or discontinuous variable, and now you get to see here this, where you get to see these two different names for the same thing. So different fields name them different things, but they're the same thing. So discrete or discontinuous is a variable that comes in whole units or categories. It's either there or it's not there. You can have, I will say this, you can have a fraction, but the fraction has to be something that's not an unlimited amount between any 2 points. So when you talk about the GPA you'll get for this class, you'll get a grade, but it'll apply to your GPA. And it'll be a 4.0, a 3.0, a 3.33, 3.67. The point is you can't get in this class something between a 3.33 and a 3.67. So it's discrete, meaning there's these separate groupings or categories. And what do I mean by it's either there or it's not there? Another way to look at this is something like the number of kids someone has, the number of children someone has. You can't have half a kid. You either have a kid or you don't. You either have 2 kids or you don't. So it's something that's either there or not there, usually expressed as some finite number. Conversely, on the other hand, you have continuous. And this is a variable that forms a continuum. And this is something that can be represented by fractions or whole units. And the big difference between the continuous fractions and the discontinuous fractions that I just explained is continuous is there's an unlimited number between any 2 numbers. So whereas I gave the example with GPA of a 3.33 and a 3.67, and you can't get between them, in a continuous, every number between them would be available. And continuous is limited just by our level of measurement, our measurement tool. So if you stand on a scale and that scale says you're 180.1 pounds, that doesn't mean you're exactly 180.1. That just means the scale goes to the 0.1. You're likely 180.15734, on and on and on and on. The point is if we had something that could measure it to a much finer degree, you would be able to get more and more decimal places. So that is the different types of variables. Let's switch now to levels of measurement. This gets us to learning objective 3, which is identify the different levels of measurement. The first level of measurement that we're going to look at is nominal. So nominal, Latin for nomen, which means name. Nominal is basically data that's in a category. We talked about quantitative versus qualitative. Qualitative or categories would be a nominal variable. It's basically the same thing as qualitative. It's the same thing as categorical variables if we're talking about that. Another term for variables are categorical variables. And nominal basically looks at the categories. So a nominal variable would be something like the manufacturer of a car. With nominal variables, the variables need to be, the categories need to be mutually exclusive. What does mutually exclusive means? That is that each individual observation, each individual thing can only fit into one category. It cannot be in 2 or more. So let's say we're looking at the manufacturer of a car. Then you've got mutually exclusive. Chevy and a Ford, they're in different categories. You're not going to have a Chevy that's in the Ford category. Chevy's got its own category, Ford's got its own category. Let's say you cut 2 cars apart and merge them together. You took the front half of a Chevy and the rear half of a Ford and merged them together. Well, now they're both a Chevy and a Ford. If that was the case, we would have to create a category that is other or mixed. And that car would not apply to the Chevy category or the Ford category, only to the other, because each individual observation can only fit into one category. It also needs to be collectively exhaustive, meaning you have to have a category for every observation. If you're counting the vehicles or you're looking at the vehicles, you see a Ford, you put it into Ford. You see a Chevy, you put it into Chevy. You see a Toyota, you put it into Toyota. Let's say you didn't make a category for Lamborghini, but a Lamborghini drives by. Well, now you either have to create a category that's other or create a category that's Lamborghini specifically. Likely you'd create an other category, but there must be a category for every observation. Important though with nominal variables is there is no true zero. What do I mean by that? I mean the numbers don't mean anything. Let's say we assigned a 1 to Chevy, a 2 to Ford, a 3 to Toyota, a 4 to other. Let's say we did that. The thing is, though, is those numbers don't mean anything. They are just an identifier. It doesn't mean that any one category is better than the other category or has a higher value or a lower value than the other category. Those numbers just mean they're an identifier. So because of that, if we applied a identifier of 0 to a category, it doesn't mean that that category is the absence of whatever it is we're measuring. That's what I mean by a true zero. A true zero is that whatever it is we're measuring, if it's got a 0, that means it's the absence of whatever it is we're measuring. An example here would be weight. A weight of 0 is the absence of weight. So that would be a true 0. When you're talking about a nominal variable, if a 0 is applied to it, it's not the absence of, so it's not a true 0. Some examples here is gender and political affiliation. So that's two different examples of nominal variables, or even biological sex. You've got these different categories. The next variable is the ordinal variable. Now, ordinal variable, we've taken a step further than nominal. And with ordinal variable, the numbers now mean something. Whereas the nominal, they didn't mean anything. Ordinal, they actually now mean something. So with ordinal variables, the numbers, what matters is the order they're in. That's where you get this ordinal or order. If you have a 1, a 2, and a 3, you know that 1 is less than 2 and 2 is less than 3. The important thing is, though, with a ordinal, it doesn't tell you how close the observations are from one another. So it doesn't say the distance between 1 and 2 and the distance between 2 and 3. It could be that the distance between 1 and 2 is less than the distance between 2 and 3. So you get this like when you're talking about like finishers in a race. Well, one person gets first, the next gets second, the next gets third. It doesn't mean the distance between 1 and 2 here is the exact same as the distance between 2 and 3. And we don't know for sure the distance between them just from the number 1, the number 2, and the number 3. So in that case, all that matters is the order, not how far apart they are. Just like with nominal, there's no true 0. If we had a 0 here, that doesn't mean that the person in the race who got a 0 at the finish, let's say they got a 0 because they didn't finish, that doesn't mean the absence of a position or the absence of whatever it is we're measuring. It just means that they were given a 0. And that 0 is before 1. So some examples here are like your class rank or the finishing positions in a race. Because in both of these, there's differences between one and another, but the differences aren't consistent. So we don't know how close or distant the observations are from each other. The next level of measurement is interval. So now we've taken that ordinal, but now the separation between each value is equalized, meaning the distance between each value is the same. So the difference between the values is now known. So if you have a 1, a 2, and a 3, the distance between 1 and 2 is the same as the distance between 1 and 3. We can still tell that 2 is greater than 1 and 3 is greater than 2. But now we can say how many units something is greater. So 3 is 2 units greater than 1 because the units between them are the same. However, there's still no true zero. Zero does not imply the absence of something. Let's say I was trying to see a home's cost above average. So let's say the average cost of a home is $200,000 in the area, and the house is $300,000 that you're looking at. Above average, it's $100,000 above average. So we apply $100,000 to it. That does not mean if we applied a zero value to a house because it's exactly 200,000, so it's no different than the average. That doesn't mean that that zero we applied to it implies an absence of what it is that we're measuring, and that what we're measuring is value or cost. So the zero there doesn't mean an absence of cost, it just means that it's at the average. So therefore, we cannot make ratio statements. We cannot say 100 is twice as large as 50. In my example, let's say we've got one house that's 100,000 above the average and another house that's 200,000 above the average. We can't say that this house that's 200,000 is twice as much as this one that's 100,000, because in actuality, this one was 300,000 and this one was 400,000. So in actuality, it's only 100,000 more. It's not twice as much more. So we can't make those ratio statements with interval levels of measurement. Some examples here, SAT test scores, because they range from a minimum to a maximum, but the minimum is not a zero. So there's not an absence of. Fahrenheit and Celsius temperature, a temperature of 0 does not mean the absence of heat. So 0 degrees Fahrenheit is not the absence of heat. 0 degrees Celsius is not the absence of heat. When we're talking about temperature, what we're basically measuring is levels of heat. A measurement of 0 on Fahrenheit and Celsius is not an absence of heat. So it is not a true zero. The final level of measurement is ratio. We take all that we've talked about before up to interval, but now we are going to apply an absolute zero. So 0 means a true absence of. With the ratio level of measurement, if you have a 0, that means that you have an absence of whatever it is you're measuring. And because of that, we can make ratio statements. We can say that something is twice. If we've got 100 and a 200, we can say that 200 is twice as large as 100. Some examples here are Kelvin temperature scale or height, specifically when measured from the ground. So Kelvin temperature scale, a 0 degrees Kelvin means the absence of heat. A height of 0 when measured from the ground means an absence of height. Let me actually use an example using height. I'm going to put a person here. My drawing skills are fantastic. We've got the ground here. But now, let's say we've got a table. And we've also got a really tall person. Let's say this person is 4 foot tall. The table is 3 foot high. And we don't even need to do a really tall person. Let's just do a person, actually let's put this person at 5 foot tall, and let's put this person at 7 foot tall. So we do have a really tall person. So we've got 5 foot tall, for the first person, 7 foot tall for the second person. These measurements that I just did are ratio, this 5 foot, because it's 5 foot measured from the ground. 7 foot here is 7 foot measured from the ground. However, let's say we were starting the measurement at the top of the table. So in this case, we measure from the top of the table, and it's 2 foot. Over here, we measure from the top of the table, and it's 4 foot. That is a interval level of measurement because a height of 0 is not the absence of height, it's just where we arbitrarily decided to start measuring. However, if you looked at it here, this person over here is 4 foot from the top of the table, this person's 2 foot, but 4 foot versus 2 foot is twice as much, but we can't say that the person on the right is twice as tall as the person on the left, because they're not. If we were measuring from the ground over here, we see that they're only 2 foot taller. So they're not twice as tall, they're just 2 foot taller. So this is how you would differentiate interval and ratio. Interval, 0 doesn't mean the absence of whatever it is we're measuring. Ratio, 0 is the absence of whatever it is we're measuring. So this gets us to some questions. Nominal, ordinal, ratio, or interval. What level of measurement are these? Marital status. So married, single, divorced, all of those. What is marital status? If you said nominal, you are correct because it is categories. Then if we applied numbers to it, if we applied 1 to married, 2 to single, 3 to divorced, those numbers don't mean anything, they're just identifiers. How about Olympic medals of gold, silver, and bronze? If you said ordinal, you are correct because these are finishing positions. It doesn't necessarily mean that the finishing position between gold and silver is exactly the same as between silver and bronze. How about hometown of students? This is also nominal because your town is it's a category. And let's say there's a few people from Lansing, somebody from Detroit, a few people from Grand Rapids, some people from some small towns. Those are categories. Number of words remembered on a memory test. Say you were given 15 words and you had to then you had to see how many you remembered after. Hopefully you said ratio, because if you remembered 0 words, it's the absence of words. Yet somebody who remembered 1 word is exactly the same difference between the difference between somebody who remembered 1 and somebody who remembered 2 words is exactly the same as somebody who remembered the difference between somebody who remembered 11 and somebody who remembered 12 words. So the intervals are the same, and a 0 is the absence of what it is you're measuring. Driving speed. Well, here you should have also said ratio because, again, the speeds, there's a consistent interval between speeds, and a speed of 0 is the absence of movement. How about IQ of your classmates? Think about that one for a minute. 100 IQ is average. Standard deviations of 15. Means 68% of people are between an 85 and 115 IQ. About 92% are between 70 and 130. Here's a tricky one. Now, I'm going to say it's interval. That is because technically an IQ of 0 isn't an absence of intelligence. You're never going to be able to get to 0. However, this is a tricky one because the way we measure it, it could be that 0 is an absence of. And at the same time, Does a difference of 100 to 110 IQ, is that the same as a difference of 120 to 130? And that's really questionable. So this is one of the reason I put this here is to show you that it isn't always clear cut what level of measurement a variable is. It could be due to the operational definition of the variable that it might be interval or ratio or any of these. So that's something to keep in mind. For this next learning objective, differentiate a parameter from a statistic, we've already covered it for the most part. I just want to go into it in more detail now. So as I said before, a population is a complete set of data possessing some observable characteristic, the characteristic of interest to the researcher. A parameter is a number applied to the population that quantifies a characteristic of the population. It is constant and based on extensive research in many samples. So parameters are very extensive, very in-depth, very hard to obtain usually. If your population is just 40 people, then it's not a big deal. So if whatever it is you're of interest, maybe you're only of interest of something that's a very rare phenomenon that occurs, and your population is those 40 people in the world that it happens to, very small, not too difficult to collect data on all of them. However, if your population is everyone in the world, that's very difficult to do. You're basically not going to be able to get true parameters for that population. That being said, based on prior research and the estimations of the population parameter from prior research, you can assume a population parameter is a specific thing. So when we get to inferential statistics later in the semester, we'll talk about differences between tests and the different tests you do. And one of the different tests is if you, one of the deciders for the different tests is if you know the population standard deviation or not. And basically the population variability, how variable the population is. And even though it's pretty much impossible to get it in most cases, you can use prior research to estimate what the population standard deviation is supposed to be. So it's something that basically takes prior research to do. But because we can typically not sample the entire population, we use samples to make inferences about the population instead. So a sample is a subset of the population, a part of the population that bears the same characteristic of the population. And a lot of researchers will get this wrong, and they'll take a subset that isn't the same as the population they're trying to reference. Let's say you're trying to reference everybody in the US, but your sample is only college students. Well, that might not pan out because college students are different in a lot of ways, characteristic-wise, than the entire US population. So it's something just to keep in mind. And then a statistic is a summary value based on a sample. So whereas that parameter is the number applied to the population, the statistic is the summary value based on the sample, and it varies from sample to sample. And then the key question that we have is the sample representative of the population? And I already mentioned this. This is a mistake a lot of people make in not having their sample representative of the population that they're making inferences about. If your sample only has college students, you can only make inferences about college students. If your sample is only from the US, you can only make inferences about the US. Those types of things. So it's very important to make sure that your sample is representative of the population that you are making inferences about. So in order to make sure our sample is representative of our population, first we have to use random sampling. Every member of the population should have an equal opportunity of being included in the sample. And as I already said, if we're doing research, a lot of college and university research is done on university students. So it's not, every member of the population is not able to be part of that sample. So in that case, random sampling would eliminate you from making inferences about the population as a whole. We also need to do random assignment. This is very important. So let's say you've got multiple different levels. We're giving people 2 different drugs and a placebo to test for pain. Each person in your sample needs to have an equal chance of being assigned to any of the groups. You can't just collect the first 20 people and give them drug A, the next 20 give them drug B, the next 20 give them the placebo, because maybe in the process of collecting, something else had happened. Maybe it was a different time of the day. Maybe it was something had happened in the country that caused people to feel differently. So because of that, you need to make sure that every single person who comes in has an equal chance of being in any of the groups. And still, you're going to run into sampling error. Sampling error always is going to occur because, as I said on the previous slide, that your value of a sample statistic can vary depending on the sample. Well, what that basically means is if I collected, let's say I collected 10 random students, and then I got their average age, and then I collected 10 more random students and I got their average age. You're not going to, or you're very unlikely to get the same average age for those 2 samples. And if I collected 10 more, I'd get a different age, 10 more, a different age. You might get overlap, you might sometimes get the same thing for 2, but it's highly unlikely. Usually you're going to have variability between your different samples. So because of that, you're always going to have a difference, or almost always going to have a difference, between your sample statistic and your population parameter. Remember, the population parameter is the true value of whatever it is you're measuring. Usually you can't get the population parameter, but we make an estimate of the population parameter based on the sample statistic. However, we understand that there's going to be a difference between the two. If you collected 10 different samples, you're likely to get 10 different sample statistics, and not one of those is likely to be exactly equal to your population parameter. So, as I said already, your sample will contain error and will not be 100% representative of the population. It is pretty much going to happen. And we'll talk about probability later and how we take into account sampling error. Because as long as you've got random assignment and random sampling, then you're taking care of random error. There's 2 different types of error we'll have in statistics. We'll talk about this later in the semester, so you don't have to write this down now, but there's 2 different types of error in statistics. There's random error and there's systematic error. Random error is good. Random error is sampling error. Sampling error is a type of random error. It just happens by chance. Conversely, you've got systematic error. Systematic error is bad error. It is error because you didn't do proper random sampling or random assignment, or some other part of your experiment was messed up and it caused you to have error. And the problem with systematic error is we can't account for it with probability. However, random error we can account for with probability. So when we talk about probability later in the semester, we'll look at how that we can then use probability to then make those inferences about the population, because we understand sampling error occurs, we understand sampling error is random, and we understand the probability of that random effects happening. Our next learning objective is to describe the main difference between descriptive and inferential statistics. Well, I've kind of already gone over this as well, but now let's look at it again in a little bit more detail. So descriptive statistics are used to organize and summarize and present data in a way that makes it understandable. We're going to cover descriptive statistics in the next few weeks. I say first half, but really it's the next few weeks. And essentially, descriptive statistics are there to summarize the data so that it is able to be interpreted. If, let's say, I gave you 10 values, 1, 7, 3, 6, 4, 3, 9, 1, 2, 4. Well, when we look at that, we can look at it and see, yeah, it goes up to 9, it goes down to 1, there's some stuff in between. The mean, the average, won't even use the word mean here, the average might be about 4, maybe. It looks like it's about 4, maybe 5. That's not great, just saying all that. The problem is that's with 10 values. What if I gave you 100 values or 1,000 values? You can't look at just the values and make any decisions about it or know anything real about it. What you do is you take these descriptive statistics like the mean, which would be the average of them, and take the actual average of them. That's a descriptive statistic that would allow us to explain the data better. You would take things like the standard deviation and the variance, which is how spread out the scores are, and that would help you with describing the data. So descriptive statistics are values that are used to summarize and organize the data. Conversely, inferential statistics is when you take those descriptive statistics, use probability, and then make inferences about the population. So when you've got, let's say you've got a sample and you get the average age in that sample, well then you use probability to say what you think the average age of the population is. And that's the inference you're making about the population. And then we're going to use inferential statistics in the second half of the course after we get done with probability. So the first exam is descriptive statistics, the second exam is probability, and then the third and fourth exam are inferential statistics. Just real quick, some types of research design. I'm not going to cover it in too much detail in this class because we're going to go over this much more in methods. But you've got experimental design, like true experiments, where the experimenter is controlling as much as possible, manipulating the independent variable, and measuring the dependent variable. But you can also have non-experimental designs. Quasi-experimental designs where you compare intact groups. So, for example, if the experimenter is assigning conditions, that's a true experiment. However, what if you're trying to see the results of pregnancy on a specific hormone in the body? Well, you can't assign people to be pregnant or non-pregnant. So what you do is you do a quasi-experimental and you compare intact groups. And there you've got people that are pregnant and not pregnant, and you compare those two groups. It's not considered a true experiment because the researcher isn't controlling everything. It could be something else that's causing certain people to get pregnant is actually what's causing this change in hormones rather than the actual getting pregnant that changes it. And then finally, you've got correlational research, and correlational research is when you're basically comparing different dependent variables. So experimental is when you're using an independent and a dependent variable. Correlational research is if you've got multiple dependent variables and you're comparing them. But we'll come back to that later. One thing when we're talking about stats that we need to talk about is real limits, called true limits or real limits. And this is what is basically referred to, or what you can look at it as, a range of numbers in which the exact value exists. So if I said, let's say, 180.1 pounds. Let's say you get on the scale and you're 180.1 pounds. Well, are you exactly 180.1? That's highly unlikely. It is very, very unlikely that you're exactly 180.1000000 pounds. You are actually going to be between 180.05 and 180.15. That's the range or real limits of the weight you actually are, because you're somewhere in between those. The scale just says 180.1 because that's the level of measurement it can come to. So how do you get the real limits? You take and do plus and minus 1/2 of the unit of measurement. In this case, let me go back up here. Our unit of measurements was the tenths place. So if we moved one farther than that, or took half of the tenths place, let's say we were looking at someone who was, let's say 68.4 inches tall. Well, again, the level of measurement is the tenths place. And that's the tenths place. That's not, we don't take the 0.4 yet. That's just the tenths place. So the level of measurement is 0.1. Because that's how fine it can get. It can go up by 0.1, down by 0.1. So half of that is 0.05. Half of 0.1 is 0.05. Divide 1 by 2 and half, you get 0.05. Now, we are going to take and add and subtract our half of the level of measurement to that 68.4. So what we get is 68.35 and 68.45 inches. And that's the real limits. And a person who measures 68.4 inches is going to be between 68.35 and 68.45. And you're going to have to do that on your first homework as well. Next thing is rounding. And anytime you've got a continuous measure, you round it to represent it as a discontinuous number. The general rule for this class is going to be to do 2 decimal places at the end of a problem. However, if you're doing 2 decimal places at the end of a problem, you should always do 2 more decimal places than that at intermediate steps of the problem. So let's say you've got 4 steps of the problem. You round the first 3 steps to 4 decimal places, and then you round the final one to 2 decimal places. The reason you do that is that corrects for rounding errors. So if you round everything to 2 decimal places, your final answer is going to probably be up or down a little bit because of rounding errors. So round intermediate steps to 4 decimal places and the final answer to 2. Unless you're told otherwise for the rest of this class, that's what I'm looking for. Round intermediate steps to 4 and then give me your final answer at 2 decimal places. Now, interestingly enough, there is a special rule in rounding that you do not have to use. If you use it on the first homework, you do some rounding. If you use it on the first homework, you'll see some times where you have to use it. But the special rule in rounding, because it's really interesting actually, and stats takes this into account. So what we do is anything that's 0.1 through 0.4, we will round it down. Anything that's 0.5 through 0.9, we'll round it up. That's the standard way to do it. However, when we look at it, we've got 0.1, 0.2, 0.3, and 0.4 there. And down here we've got 0.5, 0.6, 0.7, 0.8, and 0.9. If you see here, in 4 cases, we round down. In 5 cases, we round up. So there's a slight skew or slight bias in standard rounding rules to round up. You round up slightly more than you round down. If you're doing just a few things, that's not a big deal. If you're running hundreds, thousands, tens of thousands, millions of transactions, that slight influence towards rounding up has a huge deal. It does a lot. So the special rule of rounding that you can use, I don't expect you to use it, but the special rule of rounding is specifically when you have 0.5 that you look at what's before the number you're rounding with. So let's say you have 6.345000. It's when you're at exactly 5, and we're going to round this to 2 decimal places. And let me do 6.335000. And again, it has to be exactly at 5 with zeros after it. If you've got 6.3451, that one will get rounded up because it's above exactly 0.5. Just like 0.4, if it was 0.3449, it would get rounded down. But ignoring that, just looking at the cases where it's 5 with zeros after it, now we're going to round this to 2 decimal places. If you look, what you end up doing is looking at the number right before it. If the number is even, like it is in this case, you round up. If the number is odd, like it is in this case, you round down. And that takes into account the skew towards rounding up at 0.5. So what you end up getting is an equal amount of rounding up and rounding down. I'm not expecting you guys to do that this semester. I'm not expecting you to even do it on the first homework. But if you do, great. If you don't, that's fine. I'm going to mark you right either way. Let's get to the final topic of this lecture, and that is the summation notation. So we're going to look at that. So the last learning objective is utilize the summation notation in computations. And as I've said, and I'll continue to say, stats is not a math class, but we use math, and this is where you'll use the math. So anytime you see X or Y, that's variables used to represent observations, it'll be a variable. N is the number of scores in a data set. You'll also see it as a lowercase n. Technically, a lowercase n is sample size is the size of a sample, and uppercase n is the size of a population. But sometimes you'll see them used interchangeably when you're referring to samples. But generally, you're going to see it as a lowercase n when you're talking about the sample size, when you're talking about a sample. If you see this, X with a I next to it, and in a sense, X with, let's say, a 1, or X with a 2, or X with a 15, what that is basically saying is that's a specific observation in the data set. This is the first observation, this is the second, this is the 15th X observation. So if I had an X variable, and I had 1, 2, 2, 1, 3, 4, 7, 9, 6, 3, 2, 2, 1. How many do I have there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Let's put a couple more ones up here. 14, 15. So now this is the 15th observation in the data set, this one at the bottom. So x15 would be equal to 1. x1 would be the first data one. That one's also equal to 1. And x2 is also a 1. They all ended up being 1s that time. But let's say you've got 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the 9th observation. So x9 is equal to 7. Same is true with y. It's that score in the data set. So if you had a y variable, however that was up, whatever one it was specifically, so if it was a y1, it would be the first observation. And then the final thing to be aware of here is this. It's the summation notation. Let me write that bigger. It's technically sigma, and it is the summation notation. It basically means add everything after it, following order of operations. We'll look at some of the special rules of it and how it works, but you add everything to it. So if you did the, let's do 1, 3, 4, 2. If we did the sum of y, what we're basically telling you to do is sum all y scores. So you would add up all of these y scores together, and you get 10. So the sum of y would be equal to 10. 1 plus 3 plus 4 plus 2 is 10. So the summation notation is where you add everything after it, following order of operations. And I'll explain that more in just a minute. And that is the rules of priority. The order of operations is very important. That is the one thing in the first part of this semester that will trip up the most people, is not following order of operations. Parentheses, then exponents, then multiplication, then division, then addition, and finally subtraction. And remember to always work from left to right for each of these. That'll come up relevant in a minute when we talk about addition, because you'll have to do addition in 2 different ways. And if you follow the order of operations, you can actually end up not getting the right answer. But I'll show you that coming up in just a minute. So follow your order of operation, your rules of priority, and then within that, you end up being able to use the summation notation. Let's look at some examples and some things that are going on here. So we've got our X scores. These are our ID scores here. We've got our X scores here, our Y scores here. Let's look at this first one. Now you see some things that are a little bit different than the last slide. The last slide I just showed you this. Well, now you've got some numbers below and some numbers above. I am not, after this first homework, I'm not going to bother with these numbers above and below. All you'll ever see is it like this over here without the numbers above and below. But what the numbers above and below mean is, in this case, the I below means you start with observation 1. So if it's got that below, it means that's what observation you start with. The number above is how many observations you go. So we're starting at 1 and we're going 2 observations. So that's what you see here. It's going to be x1, so the first observation, and it's going to go 2, so it's going to go x1 and x2. So you've got x1 and x2 here, 4 plus 9, you get 13. The same thing is true with the next one, but instead of starting with 1, we're starting with 3. So we're going to start with the third observation. That's why you see this being the third observation here. And then if it has an n at the top, that means go to the end. It doesn't mean you go that many, it just means go to the end. So there's 4 observations, so you go to the end, and we've got observation 3 and observation 4. In this case, it's x squared. So you're going to square each of the x's before you add them. Again, remember, rules of priority, order of operations. You do exponents before you do addition. Summation notation is addition. So you're going to do the exponents first, x squared. So 6 squared plus 8 squared, and you end up with a score of 100. And finally, this bottom one, this is the standard one, and that is you start at 1 and you go to the end. And that equals the exact same thing as the sum of y. If it's got no numbers above, letters above, below, any of that, then it basically means start at the beginning and go to the end. So in this case, sum of y is y1 plus y2 plus y3 plus y4. So let's do some practice here. Let's do a few of these. So now, this first one, we've got the sum of 2x. And pause the video here and try it on your own, and then unpause it and see if you got it right. Okay, so first things first, you need to remember order of operations. This is multiplication. Because it's multiplication, 2x, that comes first. That comes before the addition. So what we're going to do is we're going to multiply each x by 2. So it's going to be 2 times 4, 2 times x1, plus 2 times 9, 2 times x2, plus 2 times 6, plus 2 times 8. What do we get? 8 plus 18 plus 12 plus 16. And we get a final answer of, what we got? 54. So again, remember, do the multiplication first and then the addition. Number 2, go ahead and pause it and try it on your own. Okay. Now, again, order of operations is important. We now have parentheses around the sum of y. So we're going to do that first. We're going to take and do 5 plus 3 plus 7 plus 6. We're going to do the addition first. And then we will square that. So what do we get? 21 squared. And I should know 21 squared off the top of my head. What is it? It is 441. Remember to circle your correct answer. Okay, let's do number 3 now. Take a minute to pause it, do it on your own. Okay, all of it's in parentheses now, so all of it's going to be done before the addition is done. And the y squared, again, you do exponents first, so it's going to be 5 squared minus 5. That is y1 squared minus y1. But then we need to add that to y2 squared, 3 squared minus 3, plus 7 squared minus 7, plus 6 squared minus 6. So what do we got here? 20 plus 6 plus 42 plus 30. We get a final answer of 98. And then the final one, number 4, take a second to pause it. Okay, this is that special one I was talking about a minute ago, where you got to remember to work from left to right. So there's no parentheses here. So what we're going to do is we're going to do the summation first, because it's addition, and then we're going to do the what's to the right of it, the addition subtraction to the right of it. So we're going to take the sum of x, which is 4 plus 9 plus 6 plus 8, and then after we do that, we're going to subtract 10. If you do it wrong and you do the x minus 10 first, it would be 4 minus 10 plus 9 minus 10 plus 6 minus 10 plus 8 minus 10. You're going to get a very different answer. What do we have here? 27 minus 10, or 17. So that leads us to some of the rules of summation. First off, that the sum of a constant is just equal to the number times the constant. I'll show you that in a minute and on the next slide. Next, the sum of a constant times x is equal to the sum of x times the constant. We'll look at that on the next slide. Then the sum of x plus y is equal to the sum of x plus the sum of y. And finally, the sum of x times y is not equal to the sum of x times the sum of y. Let's look at those individually. First, the sum of a constant equals n times the constant. So let's look at a case where c is a constant. What do I mean by a constant? I mean it stays the same. It never changes. It's always the same thing. It's not like a variable where x, where it's different each individual observation. It's the same throughout. So it's a constant. In this case, we're going to make the constant 10. So the sum of the constant when n equals 4. So if n equals 4, you see that here with the n equals 4, you've got 10 plus 10 plus 10 plus 10, it's equal to 40. Well, if we just did 4 times 10, same thing, the number times the constant, you get the same thing, 40. So the sum of the constant equals the number times the constant. They're the same thing. And that's just simply, why is that the case? It's because you can pull out a constant whether you add in the constant in before you multiply or multiply the constant after. Because it's a constant, it comes out the same both ways. Let's look at the next one. And this is similar to that one we did a few slides ago where we had the constant times x. So if you recall a few slides ago, we had it was the sum of 2x. So it was a constant, the 2 was a constant times x. Well, we can look at this here and also look at the fact that the sum of the constant times x, if you pull that constant out and just do the sum of x times the constant, you get the same thing. Let's look at that now. Let's say our constant's still 10, and we're doing the constant times 4. So we've got 4, 9, 6, and 8. 10 times 4, 10 times 9, 10 times 6, and 10 times 8. Add all of those together, and you get 270. However, what if we just took the sum of x, so we've got 4 plus 9 plus 6 plus 8, which is 27, and multiplied it by the constant, you also get 270. And why is that the case? Because the constant is getting multiplied in the same amount of times, or included in the same amount of times, whether it's in the problem or out of the problem. The next rule of summation is the sum of x plus y equals the sum of x plus the sum of y. So let's look at an example of that. X plus y, you've got here, in this case, x plus y, let's put it over here even though they're down here. 4 plus 5 is 9, 9 plus 3 is 12, 6 plus 7 is 13, and 8 plus 6 is 14. And if we took in, so we've got those first and then we add those up, you get 48, which is this 48 right here. However, let's say we just took the sum of x first. 4 plus 9 plus 6 plus 8, which is 27. 5 plus 3 plus 7 plus 6, which is 21. Add 27 plus 21 and you get that same 48. Why is this the case? Order of operations. No matter where you add things, it's going to come out the same. Whether you add them together before or separate, you're going to get the same thing. So why is this rule the way it is? Why are these two equal? Order of operations. The next thing is the sum of xy, x times y, is not equal, specifically not equal to the sum of x times the sum of y. Let's break that down. X times y, so this would be 20 xy, x times y. We got 27, we got 42, and we got 48. If you take and add all of those together, you get 137, which is right there. However, if you take and did the sum of x first and the sum of y first, so you get 28 here and 21 here, if you multiply those together, you get 588. Why are they different? Again, because of order of operations. In this case, you're adding first, then multiplying. In this case up here, you're multiplying first, then you're adding. So the order of operations messes up your final answer. Hopefully you understand the summation notation now. You are going to have to do it on your homework as well. Let's just do a quick note about ratios, proportions, and percentages at the end here before we get done. So if we have, let's say, 200 animals and 130 are cats and 70 are dogs. So cats and dogs. So our ratio of cats to dogs is 13 to 7. It would be technically 130 to 70. Of course, my dogs bark when that starts happening. So we've got 130 to 70. Reduce that down to 13 or 7. So that's our ratio. However, we can convert these to proportions. Proportions is a proportion of a whole. One being the whole, one being basically 100%. We can do that by taking the n, the number for each, so the number of cats is 130, dividing by our n total. So the number of cats is 130, our total n is the 200. So by doing 130 divided by 200, you get 0.65. So the proportion of cats is 0.65. You can do the same thing with dogs. You had 70 up here. Divided by the total of 200, you get 0.35. So the proportion of dogs is 0.35. And then you can convert those proportions to percentages by multiplying them by 100. And you get 65% cats, 35% dogs. That's just something that'll help you throughout the semester. As it comes up more, if you're confused, we can just address it then. This quick note gets us to that. So what did we do in this chapter? Well, hopefully you can answer these learning objectives. You can now define some of the basic terms in statistics. More will come throughout the semester. You can identify different types of variables, and we had a bunch of different types we looked at. You can identify the levels of measurement. If I gave you a variable, you could tell me what level of measurement it is. You should be able to differentiate a parameter from a statistic, at least the basics of it. Not necessarily as good as you're going to be able to later in the semester, but the basics of it. You should be able to describe the main difference between descriptive and inferential statistics. Again, in the lectures after probability, we'll go into this more, but you should be able to do the basics of this. And finally, you should be able to utilize the summation notation. Utilize the summation notation in computations. And this is very important because stats uses the summation notation a lot. You are going to use it for many of the things you do in statistics. So be sure to know how to use that. Okay, that's all I have for you for this week. Thanks. Come on back.